Okay, so here we are. The reason we were learning change of base was to solve equations. So let's take a look at how we do that. So when we solve an exponential equation, first you have to recognize what an exponential equation is. So an exponential equation has the x in the exponent versus a linear equation which has the x beside the number, and you would just do the opposite operation to solve it. When the x is in the exponent, we can't quite solve it the same way. However, when the bases are the same, the answer should be pretty logical. If I have 7 to some exponent equals 7 to the exponent 10, it should make sense that that missing number has to be 10 for those to be equal. However, if the bases are not the same, it's not quite so logical, which is why we did the whole change of base thing. So we're going to simply set the bases equal, change the bases so they're the same, and once the bases are the same, then we can assume the exponents are equal. So if I look at my first example, if I have a base of 2, that likely means I want to change 64 to a base of 2. So 2 to what exponent is 64? Well, I know 2 to the 5 is 32, so I can play around and soon I see that 2 to the 6 is 64. So I take out my 64 and I put in 2 to the 6. So it should be logical if these two numbers are the same that these two should be equal. Otherwise, this number wouldn't equal this number. So this might be a good place to pause and make sure you have that written down. Once you've got that written down, we're going to do a few more examples together. So same base is the key to an exponential equation. It always will give you a hint. So if that's 3, I want to change 27 to a power of 3. And I know 3 to the 3 is 27. So I've got 3 to the x minus 1. Got too many equal signs in there. Equals, and I get rid of the 27 and put 3 to the 3. Now that I have the same base, I can eliminate the bases and I make the exponents equal to each other. So I'm really getting rid of the bases now that they're the same and making the exponents equal to each other. Once the exponents are equal to each other, if there's anything crazy going on like this x minus 1 here, we're going to move the x minus 1 over to the other side and solve it just like a regular equation by doing the opposite operation. And you can always check to see if you're right. You can put 4 minus 1, and that would give me 3 to the exponent 3, and 3 to the exponent 3 is 27. So if I look at this one, there's my clue, base of 5. There I go putting an extra equal sign again. So I've got 5 to the exponent 2x minus 1, and I should know from previous questions that 625 comes from 5 to the exponent 4. So once I've got the same base, I can drop my base and I'll know that my exponents are equal to each other. And when I haven't got just x equals a number, I'm going to solve the equation by doing the opposite operation. So instead of subtracting 1, I bring that over and I add 1. And then instead of multiplying by 2, I'll do the opposite of multiplying by 2, which is divide by 2. So you can do 5 divided by 2 and get a decimal, or you can leave it as 5 over 2, whichever way you're more comfortable. All right, let's look at 2 more. So they get a little more tricky when both numbers are big numbers. So we have to think back to our change of base, and we've got to remember that we want our base to be our lowest number. We want the lowest base. Some hints. Even numbers usually will have a base of 2. So if I look at D, both 8 and 32 are even numbers. So I can change them out. I know 2 to the exponent 3 is 8. Don't forget the exponent that was already there, the x. And I know that 32 is 2 to the exponent 5. Just like we were doing with our change of base, because we have those two exponents, we're going to have to multiply our exponents. And to multiply 3 and x together, we get 3x. Once we got the same base, we can drop our bases, and we'll set our exponents equal to each other. And then I want to solve for x. So instead of multiplying by 3, I bring it over and divide by 3. And I can leave it as a fraction in lowest terms. Another hint, if they end in 5, generally the base is 5. And so we've seen these numbers before. We should know, hopefully, that 5 to the exponent 3 is 125. And I'm pretty sure we did 625 before, too. Don't forget the x that was there in the exponent. Same as the last question. We have a power rule. We have a base with 2 exponents. So we're going to multiply our exponents together and get 4x. Once we've got the base with an exponent, you can drop your bases. We end up with 4x equals 3. And instead of multiplying by 4, we divide by 4. So you can leave it as a fraction or you can change it to a decimal. The reason I didn't change the last one here to a decimal is because if I try to divide it, I'm going to get a repeating decimal and I'd have to round it. So this way is more accurate. All right, you're going to try some of these on your own from that same handout you're working on with change of base. I think we're talking number 2, 3, and 4. Make sure you've got all the examples copied down in your notes, and I will see how this goes.